So it's my pleasure to introduce Dr. Hyung Chang, whose research area is very close to what we are doing in Reason project, specifically around the robot-assisted dressing that Hyung focused on during his work at Imperial College. He is now assistant professor of the School of Computer Science at University of Birmingham. He's focusing on theoretical aspects of machine learning and specific problems around visual surveillance and intelligent personalized assistance. Hyung, thanks very much for agreeing to present, and can we please proceed with your presentation.
Okay, thank you, Sanya, and thank you for the introduction. Hello, everyone. My name is Hyung Chang. I'm a lecturer at the University of Birmingham, also Turing Fellow of Alan Turing Institute. I'm grateful for having the opportunity to have a talk today. The title of today's talk is Human-Centered Visual Learning and Its Applications. I'm going to introduce my recent and my previous work, or like overview of the work, and try to link to your project, the resilience or autonomous resilience part today. Okay, let's get started. So as Sanya introduced, my research background is composed of 3 components. So which is machine learning. So recently I'm using deep learning mainly. And using this deep learning technique, I'm trying to solve some computer vision tasks, which is mainly human-related tasks. And by combining this deep learning and the computer vision techniques, I've tried to enhance the human-robot interaction. To be more specific about the learning about human research, I call this as a human-centered visual learning, and which is a comprehensive understanding of human through vision. In particular, let's look at it from the perspective of robot. I'm looking at the human mainly from the perspective of robot, which is a kind of autonomous system. So I have looked into the TASS webpage carefully, and I found very interesting sentences from there. Especially these 3 sentences are very much relevant to my research, and which I completely agree that it's its importance. So the first thing is about, like humans, the autonomous system will be able to reduce uncertainty and to predict. So that's going to be one of the main part of my research. That has been one of the main part of my research. And the other part is same as you guys, the share knowledge and services with humans. Right, that's another goal. Also, cooperate with one another with the humans, and proactively seek assistance for experts. So these are very much similar my research directions and my purposes. So I'm very happy to be able to introduce my work to you, and I'm happy to take any questions or any discussions in the middle of the talk or at the end of the talk. So to be more specifically, I have 4, similarly to yours, I have 4 main questions that I'm trying to address. The first is how best to recognize a human's appearance information like posture or attribute, etc., as quickly and accurately as possible. And the second is how best to estimate hidden information of human, such as characteristics or biomechanics, or internal states as well. And the third is how best to represent a human in a form that robot, which is autonomous system, can understand based on vision. And the fourth is how best to encode a human's information to integrate a robot's reasoning system. So I'm going to show an overview about my recent works using some video result, answering or some my researches about these 4 questions. So I'm mainly interested in these 5 components of human related things, which is body pose, eye gaze, hand pose, and object pose, and environment. And I've been working on each of the topic very actively with my students, and I'm going to show some visual result for each of them. All right. Okay, let's get started. So the first part is a human body. So if the robot can understand the human's body posture, or even the more complicated articulate structure by vision, then it can be used for robot learning by imitation, or it can be used for robot object manipulation. And also, furthermore, it can be used for or provide personalized assistance. So to achieve this goal, we have started from very beginning of the cognitive system, which assume that we don't have the robot, which is autonomous system, doesn't have any model for the specific object. So we want to make it more generic. So we started from just observing the moving object, and visually, the AI system, we design an algorithm that can estimate its kinematic structure based on the motion information and the skeleton information. So this is the result. The leftmost column shows the human labeled articulated kinematic structure, and the rightmost column shows our proposed methods result. So this result, the kinematic structure was estimated based on no background about the model, no knowledge about the moving object. So it's purely based on one-shot observation. So by doing this, we can well represent moving object kinematic structure, and then it can be further being used as a kind of finding the correspondences between different objects, which can be later used for transferring knowledge from one object to the other object. To achieve this goal, we design an algorithm that matches certain body parts to the other object, or the other totally different articulate structure object body part. To achieve this goal, we have designed three new similarity metrics, which is configural structure topology. So it has to contain it to find the correspondences. The corresponding part should have the similar structure topology, and secondly, it should have the very similar kinematic movement, and the third, it should have the very similar local movement within the body. So we have done some research, some experiment. So we could find some correspondences between this box robot arm to the another the different kind of robots. So bottom right shows the local feature-based correspondences, which doesn't match. It fails to match because it looks totally different. But thanks to our kinematic structure representation of the object, it removes the very small local appearance features, but it can keep the motion and skeleton information well. So based on the motion and the skeleton information, we can find the correspondences even between totally different subjects. Here you can find the matches well, and also from upper body to the full body movement, we could match. And also, this is my favorite example. So even the human baby can mimic the crane, right? Because it looks similarly, it is similarly moving. So the robot, the autonomous system, should be able to do this kind of high-level inference, similarly to the human, right? And we have successfully implemented these algorithms, both algorithms, into the ICOP as a part of European project VisiVid. And this video shows the ICOP is bubbling its hand, and then it estimates its own kinematic structure of hand, and then later the ICOP can match its own hand to the human operator's hand by observing the human's movement, the hand's movement. And also this body skeleton estimation method can be useful for providing personalized assistance. In this example, in this work, we assume that this each person has different disability, especially for the arms. And by observing its free movement, it can estimate the humans or this disability person's comfortable moving area, and then it can find the most efficient or comfortable reasons for the human to get assisted, right? Not only the body skeleton or the motion correspondences, we also try to find the motion retargeting, which is transferring the motion information from one subject to the other subject, which is a very difficult task, even using this avatar. So in this research topic, it's one of the computer vision research topics these days. We have been using this 3D avatar, which has the same skeleton or same topology for the body, but different bone length or body ratio, which is very difficult. Even it keeps the same skeleton, because the movement will be different skeleton or body bone length will produce different movement ratio or the speed, etc. So our key idea for this work was to divide this overall movement and the frame by frame pose estimation. So, and then we designed this kind of architecture, a deep learning architecture, and we estimate overall movement and frame by frame pose separately, and then combine later using these three loss terms. So this, let me show you some result. So the leftmost column, this one is the input, and we try to transfer this avatar's movement onto here, this shaped avatar. And this is the ground truth. And the rightmost column is the state-of-the-art method, and in the middle is ours. So as you can see here, the overall movement, without overall movement estimation separately, the avatar is keep floating above the ground or sunking down the ground, because the overall shape and the position was not well estimated as time goes on. And also compared to the ground truth, ours is much more sophisticated, representing subtle movement of hand or small body part. So that was about so far I have shown you about the transferring the kinematics informations, and also the finding correspondences and the motion transfers. And I tried to go one step further, to see whether this actual computer vision can be useful for the AI, for the humans' needs. So we have we have designed a new interesting application for using body pose estimation technique, which is body pose sonification for a view-independent auditory aid to blind rock climbers. I think we can watch a short video interview about this.
Originally started to lose my sight in 2013. I was 33 at the time, and it's called macular dystrophy or macular degeneration. One of the main things I was really concerned about when I started to lose my sight was the fact that I wouldn't be able to climb anymore. I've always enjoyed climbing and found it a really good way to stress relieve and to keep fit. Some of the hobbies and things that I used to do I've had to give up, obviously, as well as driving, but climbing is one of the main and most important things that I like to do in my spare time. It's hard to explain, but it's like looking. It's like having a black dot in front of your eye, so everything I look at disappears. So at the moment I'm looking at you and I can't see the camera you're pointing at me or your face or anything else. So, but I've still got my peripheral, so I tend to, if I want to see things, I'll look up and use the very bottom of my sight to see where I'm going and things like that. And that's how I basically get around and how I continue to read with visual aids and things like that. So when I'm climbing, I can't tend to see where my feet are going. I can't see where all the holds are around me, and I struggle with most times, but especially with colours and things like that. So it's a lot easier if I've got a sight guide. I think other than using my peripheral to basically see where I'm going, I use radio headsets. So someone on the ground who's belaying can tell me where I'm going and make sure that I'm not going the wrong way. Tell me where the next hold is and the foothold is, and help me to get on that way. That's pretty much it. As well as when we're doing bouldering, which is lower stuff, things with no ropes, we tend.
Okay, so this is an interview of what I found in the YouTube, and this explains very well what's needed for this kind of system. So to enjoy the climbing as much as the people with without any disability. So far, as I said, they need some special assistant to help them to climb, and which is sometimes very expensive or sometimes very difficult to set up. So I tried to, and then we tried to replace this kind of assistance using the computational aid. So we used this moonboard, which is indoor climbing or rock climbing board, which has thousands of identical moonboard exist worldwide. And each one has different. Each one has the different set holders here, and which is located. And by combining different combination of the holders, we can design. It can be designed different route and enjoy the different difficulties, challenges. So this is the overview of the system. So firstly, we use the Kinect camera, which use RGB and depth both. And we first calibrate. We assume that it is calibrated onto the moonboard. And then we perform the skeleton tracking using RGB information only. And we used open pose. And then we projected the human, track the human body onto the moonboard space, and keep tracking its motions, its movement, and each frame we monitor whether there is any falls or whether the route completed or not, and then we keep providing the auditory feedback, and then we keep it doing this way. So be more specific. So the rock climber, because he is very close to the moonboard with this wall, we found that depth-based tracking didn't work well. So instead we use the depth. We use the RGB tracking, and as you can imagine, the body pose tracking is very noisy, especially when you use the vision. So we used a Kalman filter and median filter for removing that kind of jittering movement. And then we project the body pose onto the moonboard space, and then fall detection completed. And the important part, one of the key part of this research is providing the auditory feedback. So we have tried two different feedback methods. One is verbal feedback. So for example, we give a verbal direction. So A14 with your left hand, this is 2 right and horizontal horizontally in a line with your right hand. This is very complicated to understand, especially when you are focused, we're concentrating on the right climbing. And so we designed the second method, which is tonal feedback. Basically, it's similar to your parking sensor. If your right hand, we just give indication whether it's a right hand and left hand verbally, and then if that hand is closer to the target holder, then it gives a high frequency, and which it turned out more efficient and more intuitive to understand. So this is the system. We use the ROS, and this is the captured video, and the tracked human body pose was projected on the moon board, as you can see here. And then this left hand, right hand, left foot, right foot can be well tracked, and this indicate the next goal position, holder positions, and we check whether it is reached there or not. Right, and this one they can choose different route for their own difficulty choose. And also we have tested on the twister mat test to see whether it can be more generically applicable or not. And it found that many people enjoyed this kind of system without any difficulty, and which was published in WECB 2020. And I'm also keep continuing to represent and reading the human motions or human body and its relative body status, especially the musculoskeletal activation regression. So we have motion capture system, and I'm collaborating with the muscle expert from our School of Sports Science. And we try to keep we will be able to estimate its internal body state, especially the inverse dynamics. So calculating this inverse dynamics, it requires, as you can see, the motion capture system or this kind of marker-based system. But those are both very expensive, and we are trying to build a system that can be solved purely by vision. That's ongoing research, and one of my PhD students is working super hard on this topic. Right, that's about my research about how we can estimate and represent of the human body for the AI system. And the next is about human hand. And human hand is a very important key for the interaction because the hand is main tool for the human to grasp or interact or change the world. So my research has been focusing on 3 components of the human hand, which are the first thing is temporal information of human hand changes, and the second is human hand model, building the human hand model, and the third is interacting object cases. Today I'm going to show 2 key works. One is public ECCB work in 2020, and the other one is ongoing research. So the first thing is about sequent, which is RGB sequence-based 3D hand pose and shape estimation work. Since we believe our current pose estimations greatly rely on successive pose estimated, we aim to exploit temporal features for 3D hand pose and shape information from estimation from sequential hand motion data, which has not been available so far, because it's very expensive to annotate the hand motions without, it is expensive with the real hands. So we have decided to generate our own synthetic data set and solve this problem. So in order to generate our own hand motion data set, we first generate pose flows, which we define as sets of hand poses that are put together in a gradual motion changes during a time period. with annotations of Beacon 2.2 million dataset, which was presented CVPR in 2017. So all the 2.2 million Beacon 2.2 million datasets posed, they used some magnetic sensors and attached it on a real hand, or human hand, which means each single pose is something doable by human. It's plausible poses. It's real poses. And we plotted this 3D Beacon 2.2 million data set. Even though it is 2.2 million poses, once it is visualized using 3D t-SNE graph, as you can see on the left, there are some still, it's still very sparse. And we try to utilize this kind of data set for our research. So here's our approach on generating a pose flow. So we firstly pick on initial and the final pose, which are sampled randomly and independently from the Beacon 2.2 million dataset. Then to select the next pose station, we measure the difference between the initial and the final poses, and then update a certain amount to have a current pose updated like this. For authenticity of all poses during the variation from the initial to the final poses, we pick a pose within the Beacon dataset that is nearest to the current pose updated, which means the selected pose is a real hand pose. And we keep iterating this process until we reach we make a full sequence like this. Okay, so this shows our generated hand motion, so changes. And we use the 3D hand model, which is Mano model, to visualize these hand motion changes. And to make it, and further applying dynamic background images, we have created our synthetic hand motion dataset, which is called the SeqHand dataset. And this SeqHand dataset is the first sequential synthetic RGB hand pose image dataset, providing temporal features of various hand motions, right? And using this method, this dataset, now we are able to train a deep learning network. So as you can see here, the real hand is slightly different. Actually, it's quite different from synthetic hand. So we designed like this. Firstly, we used the SeqHand dataset to train this sequential network using a conv LSTM based sequential motion data network. And then we fine-tuned using the real hand images for better use. So this is the training objectives. So this one shows that our method could achieve the best performance in estimating the hand pose estimation. And this one shows our qualitative result. Okay, it doesn't sync left and right, but anyway, the top two. Okay, let me try. Okay, the top image shows our proposed method, and bottom shows the previous state-of-the-art method results. The previous methods are very kind of zittering its movement, and it keeps changing its motion while the shape should be the same. So more step by step we can see. So even this one is not static image. The hand doesn't move, but the baseline method is keep zittering because it's frame by frame estimation. Compared to ours is considering this motion movement, it's much more smoother. And also this kind of quick changes, it can be well handled, especially compared to this. And also the shape doesn't change much. So using this method, we have seen how we can represent, the AI system can represent this RGB hand image into the 3D shape, and it can track the hand movement well within the system. Not only this hand only, but also we are interested in the interacting object situations. So this we proposed a collaborative learning framework, but it's ongoing research. So I tried to deliver some high-level information or the idea on it. So because hand is always most likely to be interacting with the object it's holding, the holding object pose and the shape can be a good clue for estimating the hand, and also the hand pose can be a good clue for estimating the object pose and the shape. So we designed a new deep learning architecture which is collaboratively learning from each other. And this, as you can see here, our method can estimate the hand pose and the object pose at the same time, much more accurate than previous methods. So by combining these two methods, I believe it can be useful for encoding this kind of craftsman's tool usage or its own skill into the AI system. For this purpose, I think the very accurate hand pose, hand movement estimation with tool is the key for this. And I believe this will be this should be able to do this. The robot has to be able to mimic this kind of movement very fast. So that's going to be, I think, should be the ultimate goal for hand research. Okay, so the next topic is about eye gaze. So which is understanding where a human is looking at. So the eye is one of the most salient features of the human face. So the gaze shows people's desire, needs, cognitive processes, emotional states, interpersonal relations. And there are three main research topics in eye gaze research, which is the gaze following, which is reading or understanding or estimating where a human is looking at from the scene by observing the human. And the second is point of regard estimation, which is directly estimating which part of the screen, which part of the mobile device screen the human is looking. And the third is 3D gaze estimation. And the gaze estimation can be useful for assistive technology, or it can be used for gaming, or like measuring attention of user interfaces or advertisements, for training pilots and operators in cockpits, and monitoring vehicle drivers, etc. But the measuring human gaze and understanding it are both highly challenging tasks. The measuring of human gaze has been a long history. For example, the seminar work with Yarbus was carried out in the 50s, though as you can see, the measuring apparatus was complex and somewhat invasive. The newer solutions are significantly less invasive, using high resolution machine vision cameras or IR cameras, but still not easy to achieve, to get those devices. And VR, AR can be another big tool for this. And also you can see thanks to the deep learning and as the computer vision society is growing so quickly, as you can see, the number of papers has been recently drastically increased, and which reflects a very fast improvement in terms of the speed. So so far the only way we can accurately estimate the eye gaze, precisely estimate gaze is using eye tracker, either bar type eye tracker or wearable eye tracker. But as you can see, once you wear this eye tracker, it looks very geeky, and also your movement is very limited. And also, this eye tracker is super expensive. For example, in our lab we have this eye tracker, which cost more than £20,000 just for these glasses. This is very expensive. And thanks to the deep learning, the many computer vision algorithms have been developed to estimate the gaze estimation just using RGB images. But of course, the deep learning always seeks the large data set. So the MPI gaze, which collected using laptop, or this gaze capture, which collected just using mobile devices, limiting its head poses and gaze directions. So we try to we design a new method which can improve the gaze data collection environment or system. And by combining a motion capture system with eye tracker and a generative adversarial network to collect a much more general in the wild situation eye appearances. So first, a motion capture marker was attached to the eye tracker to obtain an accurate head pose. At the same time, the correct, very precise gaze vector value was obtained through the eye tracker. With this integrated sensor, we were able to automatically acquire natural eye gaze values, head pose, and appearance values. But there's one problem here. The problem is that the person's appearance is far from natural to the eye, due to the eye tracker that he's wearing. Right? So as you can see, this was solved by proposing a method of removing the area of the acquired eye images, removing this eye tracker, because we have the eye tracker's CAD model, and we generated the similar face without eye tracker. Actually, the same persons, similar head poses, the face images, and then we inpainted those removed region based on the generated images. By doing this, we can, in this way, not only can the natural gaze and the head pose vector values we obtain very accurately, but also the face and the eyes can be obtained naturally. And the data contains a much wider range. So this one shows the result, data distribution. So it shows the much wider range of natural gaze movement than any other data set, and it can be captured a much longer distance, like 3 meters. The previous state-of-the-art method of the data set was just up to 1 meter. Like this. And we adopted the ensemble learning method for the network, and we could achieve a very accurate accuracy, the high performance. So these are the results. So this one is eye tracking using the Kinect camera, and this one is eye tracking result using the normal webcam. And we also integrated this system into the wheelchair control using eye gaze. So when you look up, the wheelchair is going backward, and when you look down right, it's turning right. And when you look up again, it's going backward. And then left down is turning left, and then go straight up when you look straight. Right, so this method is already well packaged, and you can download easily by searching RTGen method. And we are keep managing this library, and this is the very recent, the GUI of this method. So as you can see here, it is captured using just the webcam, and it runs almost real time with just normal GPU. So that was the gaze estimation work. Oh, by the way, you can just search for RTGen in the Google, and you can download and test on it. And also there are some other works which is going on in my lab, which is attention level estimation using gaze information. So first, we reconstructed the classroom using depth camera, and then we tracked the students' gaze direction over the lecture. And then we projected this gaze direction onto the screen regions, which is, let's say it's blackboard or something. And then we measure the overlap, the ratio of the overlap regions. By doing this, we could estimate the student level over like 10 minutes, watching 10 minutes video. And the other thing is about focusing point guidance. So using the seeing object information together. So for here, for example, let's say we tracked the eye gaze movement on a screen, and then also we capture the object information from the computer vision technique. Then we match the closest one. By doing this, we can estimate where human is looking at within the scene. It doesn't have to be that precise, but also because it's relying on the contextual information of the scene. So which shows that whether what human is actually interested in, it can be used for understanding whether the human is what human actually wants from the scene. Plus, it can be used for understanding, the driver's attention, whether the driver actually saw the sign, or the guy who's standing or next to the street about to cross or not, or whether this guy saw the car about to enter or not, etc.
Yeah, Hyung, sorry to interrupt. We would like to have some time for questions and answers.
Sure. Yeah.
So,
sure.
so if you if you can just kind of see if you can wrap up in the next few minutes. Thank you.
Okay. Sure. Okay. Then I'm gonna quickly wrap up. I'm gonna skip some details. Anyway, I'm also working with some cognitive scientist students, which was interrupted by the COVID. But we need to read whether it's intended gaze or unconscious movement. That's another research. And also, I'm organizing international gaze workshop every year, alongside with ICCB, ECCB, Sibopia, sponsored by Google, NVIDIA, Facebook Research, Samsung. So if you're interested in gaze research, then please check the webpage, which we have already uploaded our videos, the invited talk. And also we are creating, we have created paper list. And okay, so let me skip this part. This is about 60 object pose estimation, but it's, I would say, less relevant because the human is always interacting with object, and we try to estimate the object posture to read the interaction well, like this. This is the result. And we try to go beyond to the category level object estimation. Right. So this is the last one that I prepared. I'm the human. We have entered to the new research topic, which is human understanding in the environment, which is very new, which is accepted last week to the WECB 2022. And this is novel view synthesis of a human tourist photos, because the human is always the human is always seen, but the camera is always installed one view. But we need to understand the human posture better from different perspectives, different views, which is well researched in novel view synthesis. But the previous approaches doesn't work because it requires a large data set if we want to use the nerve, which is the famous nerve, or if we want to render the humans, then the human rendering is always tricky. So we have designed a new algorithm, and I have prepared one video we can watch together.
We present novel view synthesis of human torus photos. Our framework can be split into 3 separate sections: human digitization and localization, deep buffer generation, and neural rendering. In the human digitization and localization component, we utilize a series of off-the-shelf methods to perform person detection, segmentation, and mesh generation. Additionally, we utilize a depth estimation network to estimate the human's depth from the camera to allow the human to accurately be placed into the scene. We employ a custom renderer to generate the deep buffer. This renderer handles the combination of the human mesh and the scene point cloud. The output of this renderer consists of a colored render, a depth map, and a segmentation map. Our neural renderer is built on top of that of neural re-rendering in the wild. We train the network to take in the deep buffer and transfer it into a photorealistic representation. We generate our dataset by rendering the point cloud to match the viewpoint of the referenced images from phototourism. We transfer human pixels from the reference image into the input to encourage the network to learn to pass through human data. Additionally, we normalize the color intensities of the human pixels to allow for the network to learn to relight humans. We utilize an appearance encoder network to encode the appearance of a reference image into a latent vector which is fed into the neural renderer. This allows us to accurately light the background to match the lighting of the humans. This setup allows for altering of the appearance through swapping out of the appearance reference image, allowing for synthesizing novel views with different lighting characteristics. Here we demonstrate how our method can be used to render animations of novel views.
Right, so this, in short, this on the right, this is the input image. Let's say we have photo of a parent or the son or kids, that we can enjoy the 3D shape of within the scene using VR or etc. That's what we want to do, what we have done, right? So this is conclusion. So I'm trying to achieve to answer these questions myself, and I believe my approach can be is very interdisciplinary. It can be used for healthcare or sports science or defense and security and smart factory or cognitive science purpose, etc. Right. And I give all my credits to my PhD student and collaborators. Thank you very much. Do you have any question?
Thank you, Hyung. It's that's a lot of work. Very interesting presentation. Very interesting results. I've have some work that is in the areas that you presented, but we can discuss possibly some other time. I don't know how much time we have now, but I would certainly like to encourage questions now. If anybody has any questions for Hyung. I think Colin has raised a hand, and then Shinwei. Colin, you want to go first?
Yes, sorry, I was just looking for the unmute there. Thank you very much. Really, really interesting stuff. I wonder about, and I know you've had to cover you've covered quite a lot today. The idea of the interaction between objects and humans do you think there's value in adding knowledge about the object itself in terms of our expectations of what might happen? So if we're estimating pose, for example, with a teacup, that might be quite different to if we're estimating pose with respect to a hammer. So is there value in considering how those things might influence the estimation?
Actually, that's a very, very good question. That's very high level, I think, research for the vision. At the moment, we are just, we are not there yet. So we try to, let me show you. So far, most of the vision-based 60 pose estimation is based on purely instance level. So we assume that we know this object and we have the 3D shape, 3D model of the object. So we are not there yet. And we try to push forward by using the idea that expanding to the category level 60 pose estimation. That's where we are. So this is our recent work, and this is the third paper in computer vision area. But I think that should be the way we have to go forward.
Thank you very much.
Thanks, Colin. Xinwei, next.
Yeah, can you hear me now?
Yeah.
Thank you very much for your talk. Very interesting. So my question is, I've seen your talk. Most of the data will come from the RGB sensors. So considering there's so many types of different sensors out there, are there any sensors not to replace RGB, but to support the RGB sensor to potentially make your existing result look better?
Okay, thank you. So I used to use depth sensors together, but that requires a specialized camera, right? And I think many of the challenging works in computer vision now move toward the RGB only. So that's why I recently mainly working on the RGB. But I still believe the RGBD sensor will be very much useful. It can provide more robust performance. I believe that. Also, I'm working on the tracking part, and in the tracking area, the IR sensors, IR camera is another the camera that we are going. The community is going to achieve the performance. But also the IR camera is very expensive. That's another hurdle for doing that. But yes, we are going to utilize multimodal sensors for different purposes. Yeah.
Yeah, thanks.
Thank you. Radu?
Hi, Hyung. Thank you. So this is a really impressive portfolio of research. And I wanted to ask about the accuracy of these techniques, and in particular, can you gain a lot in accuracy with pose recognition and hand position and eye gaze if you customize the algorithms that you described, or are they general purpose algorithms and their implementations accurate enough already?
All right, thank you very much. That's quite interesting question. And the performance I show is for the general person's performance, but especially the eye gaze. The eye gaze has some, it's anatomical limitations to improve the performance, because the vision sense, the center of the, there's a kappa, the angle, which shows different phobia angles, and which is human by human all different, basically. And using this vision-based method, I think the minimum error value we can achieve is 4 degrees using the general method. So removing to further improve the performance, the algorithm should be more personalized, frame by person to person, which is another very big research topic in this gaze estimation research. The same for the human body and the hand. So the human hand length, bone length the ratios are all different. And if we can make a personalized model well, then that will improve the performance a lot.
So it can actually gain a lot through this personalization. Thank you.
Yeah. But the problem is how we can do that, how we can achieve. For example, like gaze estimation, we don't have much label for, let's say, for your personalized mobile device. then only several seconds, the people want to do that, not the several days, right, to the calibration. Then how can we achieve that kind of, the fine tuning or calibration quickly? That's another issue.
All right, thank you.
Thank you. Anybody else? Any questions for Hyung now? Okay, I would like to ask something about the dressing that you showed at the beginning, and occlusions of clothes of the body posture in real time during dressing, and how did you solve that for actually finding the right movement of the robot during assistance?
In this case, we, during the assistance, we didn't do any tracking, actually. We didn't do, and also we didn't explicitly model the cloth. So we used just one cloth, which is sleeveless. And this work, we only focused on whether the robot can adapt to the comfortable zone or its movement or not. And then once it starts to move, there is no further, the interaction. But after this work, there's another work proposed, which is using force sensor of the gripper, which gives a feedback about the human's interaction, but not visually. So there's no occlusion or etc. handling by vision. This one.
Oh, okay, thank you. Yeah, so we found that occlusion of the garment it requires us to somehow predict the motion of the person or the pose of the person in real time in order to adapt the robot.
Yeah, that's a big challenge. So we try to use a kind of detour using force sensor of the holding garment.
Yeah. Yes, thank you. I just wanted one more question about the hand tracking. So I worked and published quite about hand tracking using wearable sensors. Have you tried to combine the two modalities? So we also found that even for tracking of the wearable, we need to do personalization and design based on the hand rather than that one wearable system fits all. Have you combined the two systems, wearable and vision?
We have like extensively, we haven't tried, but we have tried roughly using the kind of globe. But the glove, wearing the glove, the glove, I don't know how thick it is these days, but at that time it was quite thick, right? So it hinders its natural movement, and it's like it couldn't make this kind of poses, right? And also glove itself is quite expensive at the time. So yeah, we used to have one student who was making this kind of glove in the lab, but the glove, we found the glove is not perfect for data collection purposes or natural human movement in our case.
Okay, I see. Okay, thank you, Hyung, a lot. This was really interesting, and I think a lot of interesting things for our research as well in the recent project. So if anybody has another question for Hyung, if not, I think we can just thank you very much for your time for today and for preparing the presentation for us. And I hope we can discuss research in the future, because I think there are a lot of interlinking topics.
Okay, thank you very much. Thank you for inviting me. I also enjoyed the time. I look forward to seeing you soon.
Thank you very much. Thanks, Chang.
Bye-bye.
Thank you, everyone. See you soon.